vector space is a set along with two operations, vector addition and scalar multiplication. A vector space has the following properties. The set is closed under vector addition and scalar multiplication. Vector addition is commutative and associative. The set contains the identity vector and additive inverse for each element. Multiplicative identity exists in the field of scalars, and the scalar multiplication is both associative and distributive. Suppose V is a vector space over a field F and W is a subset of V. Is W a vector space under the same addition and scalar multiplication operations? There are three possibilities. First, W is always a vector space. That is, any subset of a vector space always satisfies all the conditions of being a vector space. Second, W is never a vector space. No subset fulfills all the properties of a vector space. And the third possibility is that W may or may not be a vector space. Which of these three possibilities are true about a subset of a vector space? The first property is false. The subset may not be closed under vector addition or scalar multiplication. It is possible that the addition of two vectors in the set W may not belong to W, or the scalar multiple of a vector in W may not be in W, or W may not contain the identity vector or multiplicative inverse for every element. So a subset of a vector space is not always a vector space. The second possibility is also false because a subset may satisfy all the properties of a vector space. As the first two possibilities are not true, the third possibility is the correct one. A subset may or may not be a vector space. It means that some of the subsets of a vector space satisfy all the properties of a vector space and some of the subsets do not. We cannot decide about a subset without explicitly verifying all the properties. A formal definition of a subspace is that a subset W of a vector space V over a field F is called a subspace of V if W is a subspace under the same operations of vector addition and scalar multiplication that are defined on V. These are the 8 properties that a subset should have to be a subspace. Fortunately, some of the properties are readily satisfied by the set W due to being a subset of V. You can say that these properties are inherited by the subset from the superspace V. Let us look at each of the properties individually to find out which properties are inherited. Floer property. This property is not inherited. It is possible that the addition of two elements of W may not belong to W, and the same is true for the scalar multiplication of an element in W. So we explicitly need to verify this property to see if W is a subspace or not. Commutativity of addition. If two elements x and y belong to W, then they also belong to the vector space V. Therefore, their addition is commutative. The addition of any two elements in the set W is commutative. This property is inherited by the subset W. Associativity of addition. The subset W also inherits this property since W is a subset of V, and if addition is associative in the vector space V, then it is associative in the subset W as well. Additive identity. It is possible that the subset does not contain the additive identity. This property is not inherited. We need to verify this property explicitly for a subset to see if it is a subspace or not. This property is also not inherited by a subset. It is also possible that an element in W has no additive inverse in W. This property should also be verified explicitly to decide if a subset is a subspace or not. The multiplicative identity is a scalar and belongs to the field F, and a subspace has the same field of scalars. Therefore, the multiplicative identity remains the same for the subset as well. So this property is readily satisfied by a subset of a vector space. If scalar multiplication is associative for the vector space V, it is also associative for the subset W. This property is inherited by a subset, and likewise scalar multiplication is distributed for the subset W. The subset W already satisfies this property as well. You see that if a set W is a subset of a vector space V, then it readily has the properties of commutativity and associativity of addition and associativity and distributiveness of scalar multiplication. Multiplicative identity also remains the same for the subset W. Therefore, we only need to verify that the subset W is closed under vector addition and scalar multiplication, and the existence of the identity vector and the inverse for each element of the subset W. Later in this video, we will prove that if a subset satisfies the closure property and has the identity vector, then every element in the set W has an additive inverse. So it will be sufficient to verify the closure property and the existence of the identity vector. Let us look at an important theorem before showing that the closure property and the existence of the identity vector are sufficient conditions for a subset to be a subspace of a vector space, and that the condition for the existence of additive inverse is redundant. You see that two zeros appear in the statement of the theorem. The vector x is getting multiplied with 0, and we know that multiplication is defined between a vector and a scalar. Therefore, this 0 is a scalar and belongs to the field F. And since the vector space V is closed under scalar multiplication, the multiplication of 0 and x is again a vector and belongs to the vector space V, and hence the 0 on the right hand side also belongs to the vector space V. This theorem says that if we multiply 0 with any vector of a vector space, the result will be the 0 vector. But what is this 0 in the field F? I will not go into detail about defining a field to keep our focus on vector spaces. Let us briefly look at what this 0 element in the field is. You remember the properties of associativity and distributiveness of scalar multiplication for a vector space? But how are the addition and the multiplication of two scalars defined? They are defined by the field F. A field is a set that defines the addition and multiplication of its elements along with other properties. So when we say that a set is a vector space over a field F, it is understood that the definition of addition and scalar multiplication of two scalars are provided by the field F. As the field F defines the addition and multiplication of scalars, it contains additive as well as multiplicative identity. Here the statement 0 represents the additive identity for the field of scalars. With this understanding of the field, let us describe the theorem again. The theorem says that the multiplication of the additive identity of the field with any vector of the vector space is equal to the identity vector of the vector space. Let us prove this statement. Add 0x and 0x together. And from the distributiveness of multiplication, we can take x out of the addition. But 0 is an additive identity of the field. Therefore, 0 plus 0 is equal to 0 again. Adding the identity vector to any vector does not change the vector. So we can write this statement as identity vector plus 0x. Now look at the left hand side and the right hand side. Using the cancellation law of vectors, we can cancel out 0x from both sides and the statement is equal to our desired statement. This is another important theorem. Let us look at different elements in the statement of the theorem. The vector ax with a negative sign represents the additive inverse of the vector ax. The element of the field A with a negative sign represents the additive inverse of A in the field F. And the vector x represents the additive inverse of the vector x. According to this theorem, the inverse of the vector ax is equal to the multiplication of x with the inverse of the scalar a, as well as equal to the multiplication of the inverse of x with the scalar a. Let us prove the theorem. Add ax with the multiplication of x and minus a. Using the distributiveness of multiplication, we can take x out of the addition. Minus a is the additive inverse of a in the field. Therefore, the addition of a and its additive inverse is equal to the additive identity of the field. And we have already shown in the previous theorem that the multiplication of additive identity of the field with any vector is equal to the identity vector. Therefore, this is equal to the identity vector. Now look at the left hand side and the right hand side. The addition of two vectors is equal to the identity vector. And we know that if the addition of two vectors is equal to the identity vector, then the vectors are additive inverses of each other. Therefore, the vector x multiplied with minus a is the additive inverse of the vector ax. Now let us prove the second part. We start with the vector minus x multiplied by a. We can write the vector x as 1 multiplied by x, where 1 is the multiplicative identity. And from the first part of the theorem, we can write the additive inverse of 1x as the multiplication of x and minus 1. Since the multiplication of two scalars with a vector is associative, we can change the order of multiplication. Now, we use a property of the field that -1 multiplied by A is equal to -A, and hence the vector A multiplied with -x becomes equal to -A multiplied with x. We have proven these two statements separately. From these two statements, one can easily infer the equality of the three vectors. We have seen that a subset of a vector space V is a subspace of V if it satisfies these three conditions. Now we will show that the first two conditions are sufficient for a subset to be a subspace. It does not mean that the existence of an additive inverse is not required for every element, but it means that if a subset is closed under vector addition and scalar multiplication and contains the identity element, then the inverse of every element also exists in the subset. The closure property and the existence of the identity element in a subset imply that the inverse of every element of the subset also exists in the same subset. Let us prove that if a subset W of a vector space V is closed under vector addition and scalar multiplication and contains the identity vector, then the subset W is a subspace of V. Let us assume that the subset W is closed under addition and scalar multiplication and also contains the identity vector. If X is any element of the subset W, then X multiplied by -1 is also an element of W. Now from theorem 2, this is equal to the inverse of X. Therefore, these two conditions are sufficient to verify if a subset is a subspace or not. The two conditions that a subset is closed under vector addition and scalar multiplication can be combined in a single condition. If a subset W of a vector space contains the zero vector and has the property that Ax plus y belongs to W for all scalars A and vectors x and y, then the subset W is closed under both addition and scalar multiplication. So the verification that a subset is a subspace of a vector space boils down to these two conditions. The proof of this statement is straightforward. If the subset is a subspace, then it contains the zero vector and is closed under vector addition and scalar multiplication. So Ax plus y belongs to the subset for all scalars A and vectors x and y in the subset. The proof of the converse part of the theorem is also very easy. Now we have a good understanding of subspaces. Let us look at some examples. The smallest subspace of a vector space is a subset W containing only the identity vector. The two conditions of the subspace are trivially satisfied. The set of all square matrices is a vector space under usual matrix addition and scalar multiplication. A subset W containing only the diagonal matrices is a subspace of the vector space of all square matrices. A matrix having all the non-diagonal entries equal to 0 is called a diagonal matrix. However, there is no restriction on the diagonal entries. The 0 matrix is diagonal and therefore belongs to the subset W. The 0 matrix is the identity vector for the subset W. It is also very easy to verify that the scalar multiple of a diagonal matrix A plus another diagonal matrix B is again a diagonal matrix. Therefore, the subset W satisfies both conditions of being a subspace. In this example, R2 is the set of all ordered pairs. R2 is a vector space under pairwise addition and scalar multiplication. The subset W of R2 contains only those ordered pairs whose member elements sum to 0. The ordered pair 0, 0 is the 0 vector and belongs to the subset W. To verify the closure property, suppose that ordered pairs x and y belong to W and A is a scalar. The sum of x1 and x2 as well as the sum of y1 and y2 is equal to 0. Calculate Ax plus y. Now the sum of the elements of the resulting ordered pair is equal to 0. The resulting ordered pair also belongs to the subset W and therefore the subset W is a subspace of R2. This example is a generalization of the previous example. The vector space Rn consists of ordered n tuples, and the subset W contains only those ordered n tuples whose elements sum to 0. The subset W is a subspace of Rn. In this example, we will see that intersection of any number of subspaces of a vector space is a subspace. Suppose W1, W2, W3 up to Wn are n subspaces of a vector space V. Since all the Wi's are subspaces, each of them contains the 0 vector, and therefore the intersection of w1, w2 and wn also contains the 0 vector. Now let us verify the closure property. Suppose x and y are two vectors in the intersection of the subspaces and A is a scalar. This implies that x and y belong to each of the subspaces w1, w2 and up to wn. Since all the wi's are subspaces, the combination ax plus y also belongs to each of the subspace w1, w2 and wn. This implies that ax plus y also belongs to the intersection of all the subspaces. The intersection of the subspaces satisfies the conditions of being a subspace. What about the union of two or more subspaces? I leave it as an exercise for you to check whether the union of two or more subspaces of a vector space V is a subspace of V or not. In this example, we will see an important definition of a vector space called the direct sum of two subspaces. If W1 and W2 are two subspaces of a vector space V, then the set W1 plus W2 is defined as the addition of two vectors, where the first vector belongs to the subspace W1 and the second vector belongs to the subspace W2. It is very easy to verify that W1 plus W2 is a subspace of V. Now we will see that what is meant by the direct sum of two subspaces. A vector space V is called the direct sum of its two subspaces W1 and W2 if V is equal to W1 plus W2, that is, every vector of V can be written as the addition of two vectors where the first vector belongs to W1 and the second vector belongs to W2. And the second condition is that the two subspaces W1 and W2 have no common element except the 0 vector. V is a direct sum of W1 and W2 is denoted by W1 circled plus W2. This is the last theorem of this lecture. This is about the direct sum of vector spaces. V is a direct sum of its subspaces W1 and W2 if and only if every vector in V can be uniquely written as the addition of two vectors, where one vector belongs to the subspace W1 and the other vector belongs to the subspace W2. V is a direct sum implies a unique combination for every vector of V. V is equal to W1 plus W2 is the only way V can be written as the addition of W1 and W2. In this part of the theorem, we will assume that V is a direct sum of the subspaces W1 and W2, and our target will be to show that V can be uniquely written as W1 plus W2. The theorem is of if and only if type. Therefore, the converse of the statement is also true. It means that if V is equal to W1 plus W2 is unique for every vector V, then V is a direct sum of W1 and W2. In the converse part, we will start with the assumption that V is equal to W1 plus W2 is unique for every vector V, and we will prove that V is a direct sum of the subspaces W1 and W2. Let us prove the first part of the theorem. Suppose V is a direct sum of its subspaces W1 and W2, and by contradiction suppose there exists a vector in V such that V can be written in two ways as the addition of vectors from the two subspaces W1 and W2. This implies that W1 plus W2 is equal to x1 plus x2. By adding the inverse of x1 and the inverse of W2 on both sides, we have the equation. Here the statement W1 minus x1 means W1 plus the inverse of the vector x1. W1 minus x1 is a short way of writing the addition of a vector with the inverse of a vector. Since the vectors W1 and minus x1 belong to the subspace W1 and the vectors x2 and minus W2 belong to the subspace W2, W1 minus x1 again belongs to the subspace W1 and x2 minus W2 belongs to W2. Now both vectors are equal and belong to two different subspaces. Therefore they also belong to the intersection of the subspaces. But we have assumed that V is a direct sum of W1 and W2, and by definition of the direct sum, the intersection of W1 and W2 contains only the 0 vector. So both of the vectors W1 minus x1 and x2 minus w2 are equal to the 0 vector. And by adding vector x1 on both sides of the first equation and adding the vector w2 on both sides of the second equation, we conclude that w1 is equal to x1 and w2 is equal to x2. So we cannot find two vectors other than w1 and w2 such that their addition is equal to the vector v. Now we will prove the converse part of the theorem. Suppose every vector in V can be uniquely written as w1 plus w2, where the vectors w1 and w2 respectively belong to the subspaces w1 and w2. Again, suppose that w is a vector in the intersection of w1 and w2. This implies that w belongs to the vector space V as well as the subspaces w1 and w2. We can write the vector w as the addition of two vectors, the 0 vector and the vector w itself, where 0 is from the subspace w1 and w is from the subspace w2. We can also write the vector w as the addition of the vector w and the 0 vector, where the vector w belongs to the subspace w1 and the 0 vector belongs to the subspace w2. In the first case, the 0 vector is from the subspace w1 and vector w is from the subspace w2. And in the second case, the vector w is from the subspace w1 and the 0 vector is from the subspace w2. But the vector w belongs to the vector space V as well, and we have assumed that every vector of V can be uniquely written as the addition of two vectors, one from the subspace w1 and the other from the subspace w2. This contradiction can only be resolved only if the vector w is a 0 vector. We started with the assumption that every vector of V can be uniquely written as the addition of w1 and w2, and we have proven that the intersection of the subspaces w1 and w2 contains only the 0 vector. Therefore, V is a direct sum of its subspaces w1 and w2.